All right, so now we have Luke speaking, and they're going to tell us about the ages of exoplanet host stars, and in particular about rotation and lithium in the Kepler field.
Thank you. Good morning, everybody. My name's Luke. I'm a postdoc just up the street at the Carnegie Observatories. And today I want to talk about two methods for measuring stellar ages. One of them is using stellar rotation, which we can measure in light curves. The other is using stellar photospheric abundances of lithium, which we can measure from spectra. Now, I'm going to talk a lot about methods today, but I don't want to lose sight of what I see as the big picture, which is that good evolutionary stories require good ages. This is the case in all areas of science. In the earth sciences, we count tree rings and layers of ice. In the solar system, if we want to measure its age, we measure abundance ratios of lead and uranium. And one tool that we have in astronomy is open clusters. We can study the properties of stars in open clusters in order to figure out the timescales over which planets and stars and really the galaxy evolve. Now, quick show of hands here. How many people have seen a plot like what I'm showing here before? I have stellar rotation periods and temperatures of a bunch of stars in open clusters. Okay, I'm seeing maybe about half the room. So if you haven't seen a plot like this before, this is a lot of data all at once. So what's happened here is many people, this long list on the side, have gone and used K2 and TESS and Kepler to measure the rotation rates of stars in open clusters. And what they see is what's been known for a very long time. The youngest stars spin faster than the older stars. Stars spin down through time. Now, there are good physical reasons for that. I want to focus on the implications for age dating. Okay, the implications that I see for age dating are that if you have a field star there, it should be between 1 billion and 2.6 billion years old. Gyrochronology by interpolation should work. You can be a little bit more precise than that statement, though. All right, the width of this sequence tells you that the star is maybe 3 sigma older than 1 billion years old. So this is an important insight. The scatter in the calibration sequence sets the limiting precision for the age dating method. A corollary is that if your star is over here, you're not going to get a precise age. Okay? It could be 300 million years old. It could be 1 billion years old. You can't say. Now, this point, for a long time in gyro models, has been ignored, partially because the data haven't been good enough to really justify treating it. But now we have these amazing sequences, and we can see that the massive stars are spinning down. They're converging to this slow sequence before the cooler stars do. The cool stars seem to later. Cutting straight to the point, there's a model now, I wrote it, that deals with this problem. So you can marginalize over the range of rotation periods that are accessible at any given age. It's just statistics. And so for this star, you get a posterior probability distribution that's highly non-Gaussian. It's broad, but it's accurate. Now, I can spell out the details just a little bit more about what this model is, how it works. I call it gyro-interp because it's gyrochronology by interpolation. And the idea is you interpolate between these cluster sequences. You fit some model to the scatter around the mean evolution, and then you apply Bayes' theorem. So you calculate the probability of a given age, given the rotation periods and temperatures and their uncertainties, and then marginalize over the intrinsic scatter. So what I mean by fit the scatter of the sequences is shown here. So at 80 million years, 120, and 300, the stars are converging to the slow sequence in an effective temperature-dependent way because the pre-main sequence contraction timescale depends on the stellar temperature, or mass. The model you can fit is very simple. This is the simplest possible thing, really, that matches the data. You have a normal distribution around the slow sequence, a trailing uniform distribution, and then a logistic function that is going toward cooler and cooler stars through time as the stars reach the main sequence. Okay, so it's a few free parameters, and basically you tautologically reproduce the spin down that's observed in open cluster calibration stars. If you want to check it out, it's on GitHub. There's documentation. Okay, before I tell you about what I see as the main application of this code, I want to talk about 3 important caveats, which I have so far not discussed. So firstly, I've assumed no binaries. By a similar token, no hot Jupiters. So the reason for this is that, sure, you can have tidal effects that influence stellar spin-down rates. You can also have other effects, even widely separated binaries that seem to be too far apart to have tidal interactions. Empirically, they show anomalous spin-down. The physical reasons for that, if you're interested in, you can find me later. But what that means is that really, if you're doing gyrochronology and you want to believe your age's accuracy, you probably shouldn't be using binaries. At least binaries within a few AU. Okay, second point, I'm talking about FGK stars that are younger than 4 billion years. So M dwarfs have been treated by other groups in better ways. Older stars as well show very interesting behavior in their spin down. There's probably a stalled spin down effect that happens for sun-like stars beyond the sun's age, and that influences the precision of gyrochronology. And finally, I'm assuming solar metallicity. All of our calibration open clusters are near solar metallicity, and it's expected that stellar spin down should be different for high metallicity and low metallicity stars. So these are all really important. Now, okay, what's that application? The application is the Kepler field. So Kepler detected rotation periods for oodles and oodles of stars, right? Like 45,000. So you take that sample and you throw out half of it because of the binaries and because of the metallicity outliers. So you do your best to select a sample of FGK stars that are single and that meet all these criteria. When you do that, the 2D histogram of rotation periods and temperatures, which were measured by other folks, by Angela Santos, by Amy McQuillan, temperatures from Travis Berger, they look like this. And just by eye, you can already tell that the age distribution that we're going to get will not be uniform, because there's a pileup right here. Now, the model on the right, this is just draws from my rotation evolution model. The point is that if the lines are separated, you're going to be able to distinguish the ages. If they're not, you won't. And you can combine these rotational ages with lithium to see, at least in certain regimes, whether they agree with each other. So now, lithium, you can play the same game. You do lithium ages by interpolation. The model that does that is called EAGLES. It was written by Rob Jeffries. And lithium is sensitive as an age diagnostic in this type of way for K-dwarfs over the first 500 million years of their lives. Okay, after that, it doesn't change very much what you can measure in the data, and so you can't use it to get precise ages. Now, for Kepler specifically, the lithium analysis is really only focused on the planet hosting stars, for which we have high resolution spectra, but it's still an important cross-check. The more important cross-check that's possible now for Kepler comes from the cluster data. Okay, there are 5 open clusters in the Kepler field, 2 of which have been known forever, and 3 of which are entirely new from Gaia. So the new ones from Gaia, Cepheus Hercules, Mélange 3, Thea 520, are all below a few hundred million years. And then the other 2 are much older. So what you want is to have your stars in these clusters near the 1 on this line, which means that your ages, whether they're rotational or isochronal or whatever method, agree with the cluster age. And you can see how hard stellar ages are, right? This is a factor of 10 off from the true age up here. And basically, we can get accurate ages, but not precise ages. That's the upshot of this plot. OK, I want to talk about the 3 main actual astrophysical results after talking about a lot of methods and calibration and verification. OK, the first astrophysics result is that the age distribution of the Kepler field is not uniform. And you can quantify that. Young Kepler stars are anywhere between 3 and 5 times rarer than their 3-billion-year-old counterparts. We can go out to this far, and the rotational census is incomplete past that. Now, the really thin blue line, this is what you get if you just take all rotation periods from Kepler. The thick blue line is what you get if you then throw out half the stars because you have real indicators for their binarity and their metallicity. Even using all of the available indicators, you're going to miss some binaries. So this is important. The sort of sensitivity that we get from using RUI or Gaia nearest star catalog, all this kind of stuff, it's not sensitive to low-mass binary companions that are close to stars within, say, 1 AU. If you correct statistically for such systems, basically you get a power law age distribution over the past 3 billion years, which agrees with some previous literature, and the stars, the planet hosts, and the literature are pretty much all in agreement. Okay, so that's the first point. The age distribution isn't uniform. Young stars way rarer than stars 3 billion years. Second point, why? Okay, there are 2 possible reasons. One is that the age distribution, the star formation rate as a function of time, could have been decreasing. The other is that maybe kinematic effects can kick the average Kepler star much higher than a typical star would be in the disk. So this is what this is showing. The average height of a Kepler star is 230 parsecs above the midplane. And the upshot of these plots is that if you compare against synthetic simulations, kinematic heating, this orange line, doesn't explain the overall slope that we see. You need to invoke both kinematic heating and a time variable star formation rate. Okay, final point. What about the ages of the planet hosts? So if you query the NASA Exoplanet Archive today, and you ask for precise ages of exoplanet hosts below 1 billion years, this is the sample. And most of these detected exoplanets are stars in open clusters, because the ages are precise, they're reliable, makes sense. This is also a very biased sample, because open clusters dissolve over of order 100 million years. So if you want to expand the census for demographic work over the first 1 billion years, you probably need to consider the ages of field stars. And if you do that, you can get something like a 2 to 3-fold expansion. Okay, I'm going to wrap up because I'm at time. I think the point from all this analysis that really surprised me the most was that even though Kepler only looked a little bit above the galactic plane, there was a huge bias in the age distribution of exoplanets that we got from the mission. Okay, so other missions are going to look in other directions. That opens a whole lot of new planetary populations, both old and young. Thank you very much.
All right, questions for Luke? We'll go ahead and go down here with Dan.
Thanks, Luke. Dan Huber, Hawaii. So the Kepler target selection was complicated. So what about the stars that weren't selected? Are we sure, in other words, are we sure that the age distribution of the stars that were actually observed are representative of the field in the Kepler direction?
Could you say a little bit more about any specific selection biases that went into the Kepler selection?
I wish I could. It's complicated, right? So binaries, for example, close binary. Adam, I think we'll talk about this a little bit. Close binaries in the kick that weren't quite resolved were probably thrown away. And so I guess the underlying question is, are we sure that the age distribution that we're inferring from the stars that were observed is consistent with the field population? And perhaps the astrophysical implications are small of this, but it doesn't change the fact that the stars that were observed. But what is?
I think it's certainly the case.
Look, we had a comment on your question.
A brief comment?
So the way that the stars were selected, right, is the Kepler input catalog was all photometry, and then they modeled out what the log G was, they put on the HR diagram of log G versus temperature. And then they selected, based on that, could they detect Earth-sized planet around what they think the size of the star was, and then they prioritized by that. That's how the selections were done.
Yes.
So,
I'm
it wasn't
aware.
by brightness or anything. I mean, so they filled so they filled out as bright as they could go, and then when they still had more targets left to do, that they then went fainter. So it was this ad hoc building of the target list.
So it's certainly the case that if the Kepler field hadn't tried to select against, say, evolved stars, then you would have gotten a different age distribution. To the extent to which Kepler's selection function succeeded at its intended goal of selecting main sequence sun-like stars, the age distribution that's observed from this type of analysis is more or less in agreement with what you can get from the simplest trilegal modeling. I think one of the, when I was doing that modeling, one of the things that stood out to me is that the agreement's pretty rough. And there's probably more work that we need to be doing in modeling different stellar populations in the galaxy in order to really answer this in detail. Like, how did the selection function for the mission propagate to the expected age distribution? I don't think anybody treated that before Kepler. There are lots of new missions now for which that might be worth thinking about.
Okay, we're going to have to thank the speaker again.